Ever wonder how developers know if their code is going to be fast or, painfully slow? Well, they actually have a special language for it. And today, we're going to unpack one of its most important ideas, Big O notation. It's how they can predict if an app is going to fly or totally crawl once it has to deal with tons of data. To really get what this is all about, we don't even need to look at any code. Nope. Let's just start with a simple thought experiment. Okay, I want you to imagine a phone book, but not a normal one. I'm talking about one that's the size of a small car. It's huge, and your job is to find one single name, John Smith. How'd you do it? No, really, just take a second. What's your strategy? So you probably didn't think of method A, right? The brute force way, just starting at the very first page and reading every single name. Of course not. Your brain instinctively jumped to something like method B, the smart search. You open it up to the middle, you see you're in the M's, so you know Smith is later. You keep cutting the problem in half. We all know the smart search is faster. But the real question is, how do we describe how much faster it is, especially if that phone book grows from the size of a car to the size of a house? And this right here is the absolute core of it all. You could have a supercomputer using that slow brute force method, and it would get absolutely crushed by a 10-year-old laptop using the smart search. The strategy, the algorithm is what really counts, way more than raw processing power. So, how do computer scientists actually talk about these different strategies? Well, they have a formal language for it, and that's where Big O notation comes in. All right, so that's the textbook definition. Sounds a little academic, right? Let's break it down. The only words you really need to focus on are performance and worst case. Big O is just a standard way to talk about the absolute most work an algorithm might have to do to get the job done. Now this is a much better way to think about it. Big O isn't about timing things with a stopwatch. It's not about seconds or minutes. It's about measuring the rate of slowing down. It answers the question, as my job gets bigger and bigger, how much slower is this thing going to get? And here's why it's so powerful. Big O is all about the big picture. We ignore seconds, because that changes from computer to computer. Instead, we count the number of steps or operations, and we only really care about the trend as our input, which we call n, gets massive. So if you have an algorithm that takes, say, n squared plus n operations, when n is 1,000,000, n squared is a trillion. That extra n is just a drop in the ocean, so we just ignore it. We only focus on the part of the equation that's truly driving the growth, the part that's making things get out of hand. Okay, enough theory. To make this feel a little more real, let's take a trip to a giant library. The total number of books in this library, that's our input size n. First up, we have O of 1, or constant time. This is the dream scenario. It's like you have the book's exact code number. You just walk up to the librarian, give them the number, and they grab it. It doesn't matter if the library has 100 books or 1,000,000,000 books. It takes the exact same amount of time. It's the gold standard. Next, O of n, or linear time. Hey, this is our brute force search from the phone book. It's like you have to scan every single book on a shelf to find the one you're looking for. If the number of books, n, doubles, well, your search time doubles. It's a straight line. Predictable, sure, but it can get pretty slow. Now for O of log n, or logarithmic time. This is where the magic happens. This is our smart search. Instead of checking every book, you just keep cutting the problem in half. You go to the middle of the library, figure out which half your book is in, and then you completely ignore the other half. Think about how wild that is. If the library doubles in size, it only takes you one extra step to find your book. It's just mind-bogglingly efficient. And finally, O(n) squared, or quadratic time. This is the danger zone. This is where algorithms just become unusable. Imagine your job is to find any duplicate books in the whole library. To do that, you'd have to take the first book and compare it to every other book. Then take the second book and compare it to every other book. You see where this is going? The workload doesn't just grow, it explodes. The number of steps is the number of books squared. So that library analogy is helpful, right? But nothing, and I mean nothing, drives this point home like seeing the raw numbers side by side. Just look at that last column. For 1,000,000 books, O of log n, our super efficient smart search, takes about 20 steps. Not bad at all. O of n, the linear scan, takes 1,000,000 steps. That's a lot, but okay. But O of n squared, it takes 1,000,000,000,000 operations. 1,000,000,000,000. That's not just slow, that's this will never finish. And this is the core takeaway. For a tiny little list, who cares? The difference is nothing. But as the scale grows to what we see today, millions of users, billions of posts, trillions of data points, your choice of algorithm is literally the difference between a working app and a crashed server. So let's bring this all home. If you're not a programmer, why should any of this stuff matter to you? Well, because Big O is the reason the apps and websites you use every single day can even exist. A social network finding your friends, a streaming service recommending your next show, a search engine finding an answer in milliseconds. All of these things rely on incredibly efficient, super scalable algorithms that can handle unimaginable amounts of data without just breaking. So let's just quickly review the big ideas. Constant and logarithmic time, that's the goal. They scale beautifully. Linear time, it's pretty good, very predictable. But quadratic time, that's a huge red flag. It's a sign that your program is going to hit a wall. Big O isn't just theory, you see. It's a really practical tool for building things that can actually survive in the real world.
So I'll leave you with a final thought. The next time an app on your phone is taking forever to load or a website feels really sluggish, maybe I'll stop and wonder, I wonder what kind of algorithm is running under the hood. I wonder what its Big O is.